So if you all would please open G2 Pixel Instruments. And so we're going to go here. If you would like, it actually doesn't matter because we're not using it any further. But if you'd like to add another 2 on there, you're welcome to. But again, the first part is where you save it. Again, we're going to go through the whole history of what we've been doing. So we want all the images that we've processed so far. So we want all the extrinsics for them. We want the location of where the images are. Again, here's the T and the elevation. So, you know, the reason why we're doing this again is that we're basically replicating exactly what we did in G1, except instead of doing the whole image, we're just specifying parts of it. And so we're only going to pull out some data. And there's tools to plot this data as well. So this is our instrument information. So first we want to pick a grid that we're going to pull this all off of. So that's the original grid that we made. So we need to know in this particular instance, the instruments that we are calling are going to have to be the same resolution as our grid and similar extents. So if you do something outside your grid, it's not going to show up. Again, if we want to define in local coordinates, so this, I give examples of each different type. So the first one is the pixel instrument type grid. So we have our dx, dy. So again, this is just going to subsample every 5 meters. Going to basically subsample our grid. Our X limit is 5. Our X lim is between this area and local coordinates. And then this one, you could just leave blank if you want to interpolate it from your actual grid. So in a longshore transect, this is one that's going to go in the Y direction. You basically specify where the X coordinate of your transect is going to be and how far you would like it, as well as the resolution. So sorry, I was mistaken. The grid only really defines the extents, not the resolution. And then run up, you would want an X transect, cross-shore transect. And again, you picked the longshore coordinate you wanted and then line it up. And then this is multicam. So after we define that, we just hit run. And so what it's going to do is it's going to plot where your instruments actually are. And then, so here, the blue is our grid instrument. So you can see it there. Our yellow is our cross-shore transect, and then our longshore transect is in red. And so then it plots the example products from it as well. So this one is our cross-shore transect. So you can see that we have, let me pull that back up again. So it started from here and it went out offshore. So you can see down here we have our beach, and it goes offshore. And then as we move up in time, we can actually see the wave crest coming in. So you imagine that this is the front of the wave coming in at that cross-shore location and receding, and then another wave coming in. These take time to interpret. And so if you kind of even imagine, I think as Meg was saying, you can see this line here. So if you were to draw a line across here, you have distance and over time, so you could get a speed or a wave celerity, something like that. That's kind of just the fundamental of all of a lot of what we're doing here. The longshore one, in this particular instance, because we're doing such short time, and it's not necessarily a great example, it's a little harder to read, but it's very similar where I flipped it, where we have our Y coordinate, and then we go in our Y coordinates here, and we go in time in the X axes. And so this is not the best example, but just to show an idea of how that looks. But again, this is this is just a printout of our subsampled grid that we did, or our CBATHY grid. So like if we were doing a pixel instrument and we were going to input this in CBATHY, this is what the resolution would actually look like. And Rob will go into more detail about what resolutions you need and what are appropriate. I've had a lot of questions, particularly from Tina, on taking this product and actually getting it formatted into CBATHY. So one reason we didn't format this exactly to input into CBATHY is we wanted to leave it a little agnostic so people could do whatever they wanted with it. I do have functions that I've built myself to try to format it into CBATHY, and you can come chat with me if that's ever your intention to use this toolbox to do that for. But also the Pixel Instrument Toolbox does that as well.
It's like, be careful if you're using West Coast beaches.
Yes.
You need to flip it.
Yes. So that when your local coordinate system, that's the important part. Yes. So I think I'm doing do we have a break or are we still going through?
Yeah, we're going through.
Okay. So our last one is multi-camera stations. So these are multi-camera fixed stations. So we'll go into this real quick. When we incorporate kind of the basis when we do all the cameras together, we're going to rectify everything on the same grid. So we're not doing a separate grid for each camera. We're going to make a grid big enough, and then we're going to try to kind of average all of our rectifications together. That's essentially what we're doing. Now, Rob has developed, along with John, kind of an averaging or a feathering, a weighted average of these rectifications together to help with these seams. But that's essentially what the toolbox is doing. We take a really large grid, and we rectify one image in one camera, and we get a lot of black area. We rectify a second one, and then if you imagine the black areas are zeros, if we kind of add them together and then average, the zeros come out, and then we get a nice, we don't consider the zeros, we get a nice full image. So ultimately, we're going to do this, we use the same tools that we've been using for the single camera. It pulls the intrinsics, it pulls the extrinsics. The big difference is we use the same function, use image rectifier, except now our input is like in a cell. So instead of just having a cell structure, instead of just having one image, we have 6 cameras, we have a cell of 6 entries with 6 images, and we'll kind of go into that a little bit later. So this is just about how we do the seams. Again, the feathering technique. This actually requires the image processing toolbox, which I didn't realize. So that is one of the errors that we are seeing in that function. Again, so if we were going to go through and process this for a fixed station, we would build our grid, and then because our camera station is fixed, we could skip E and F, and we go into G1 and G2. And so we can actually use those same exact scripts as well. So I'm just gonna, this just runs through everything. So we'll just pop through here. And so if we go into G2, so we've actually already just run, or actually let's go to G1, I'm sorry. So we're going to run this very similarly, except we're going to uncomment a bunch of sections that's basically going to overwrite everything that we wrote earlier for the UAS data, but we'll sit and kind of chat through what we're overwriting. So if you go into lines 167 and 188, we'll uncomment those. So we'll kind of start. So we change our out name because we're doing a different demo. We're going to save it somewhere else. And so you can see here where we had the IO-EO path to direct where our camera intrinsics and extrinsics are. We actually have a cell. Now we have one for each camera. So 1, 2, 3, 4, 5, 6. And so we have a file for each camera. So, that's when we did that calibration. We do it for each camera. And so those files are actually already saved in our multi-camera demo under extrinsics, intrinsics, so they're all sitting here. We actually have an image directory similarly, so collection data in each folder. So we did that as well. So for the first camera, corresponding folder, second camera. We provided a T-vector, what time each images are. Now you can do that in a clever way. I just did this as simple as possible, but you could have it read the file names. You could have it do a lot of different things. And then here is the elevation for each point. So for the UAS, we were collecting with 5 minutes, so the tide isn't going to change much. But for these fixed camera stations, these are hourly images, or so the tide is going to change. So here to keep it simple, we just have it entered. For my own workflow, like I have functions that will pull the time, go to the NOAA server, pull a water level, automatically put it in. So there's a lot of different things you can do in that regard. So after all these are run, uncommented, you can just hit enter, and it's going to do exactly the same thing. It's going to do frame 1, frame 2. Now you can see it's taking a little bit longer because it's doing the rectification 6 times for each frame, because we have 6 cameras. So this is duck, and so here is our darkest image, here is our brightest image, and here is our Timex. And then again, if you go into our output folder, you can kind of go through this. I don't know why it does that. So that is for the image products. For the image for G2, we do something very similar where we just go down. So we're going to keep all of our instruments actually the same. We're going to go down and uncomment this. Now granted, like I'm using the same grid as we did as the UAS data, just because we filmed it in the exact same location. So that's one reason we're using the same grid. But again, this is the same thing where we just add the paths to the intrinsics and extrinsics. We add the paths to the image directory and the tides and the date. And so that's how you run it differently with multi-camera data. You're essentially just running the function image rectifier with a cell instead of a single image. And so here, this is our peer data. So let me pull, where did that go? Yep, so this is our pixel instrument actually. So we actually show it projected for each individual camera. This is, there we go. So you can kind of see where there's some overlap and it will output your product. So like your grid, it will output it as one grid. It's not going to separate into cameras for you. It's just going to give you as if it came from one single input. So here's the one with our cross short and a long short transect. And you can see our other transects. So we don't even go into that 6 camera for this example. This is our example CBATHY grid we pulled. And so this is a long short transect. So you can see the pier doesn't move. And then here is our cross shore, and you can see the effect of the tide. So you can actually see the water level is coming up and the beach width is getting smaller. So that is generally the toolbox. I encourage, what time is it? Oh, I guess it's on. Okay. So we don't have anything else, right? Yeah, we could do. Okay. So before we kind of end, I think Meg's I think we'll take a break. Is that good? Or do you guys not want a break?
It's short.
Okay.
Do station design and then.
Okay. So I would encourage everyone just to play with the different steps, change grids, rerun everything, move forward. Tomorrow, well, I guess we'll have closing remarks, so I'll just do that stuff later.
All right, so we skipped one thing around lunchtime because we were afraid we were taking too long, but now it looks like we have time, so we'll go back to it. And that's our station design toolbox. Gonna just pause the recording here for a sec.